boys and girls. Oh, I gotta put the screen down. We're gonna learn about one-sided limits and continuity. Okay? So this little minus sign here means the limit, Fred, the limit as x comes from the left side. And this thing here, it doesn't mean positive c, it means as x comes from the plus side towards c. So, and this means the limit, okay? So if I look at this, does anyone know how to get rid of these little squiggly lines? I don't know what those are. What?
Left click on your mouse and then say move.
Left click on? Yeah. How do-
Probably have to turn off like spell grammar check or something.
Wait. It's okay. Okay. So all this means is you're taking the limit as x comes from the left, and this means you're taking the limit as x goes from the right, and this thing is the limit. So if I'm looking at this particular function up here, which by the way is an absolute value function, okay? If x goes towards 0, well, we'll worry about that in a second. What's the limit as x comes to 0 from the left? What number am I approaching? 0. Okay, does everyone see why that is 0? Because the y value that I'm approaching as I'm on this line from the left is 0. What's the limit as x goes towards 0 from the right? 1. Okay? It turns out in order for something to have a limit, it has to approach the same value from the left and from the right. So the limit as x goes to 0 is said to be d n e, does not exist. Okay? Even though the left, you could have a left-handed limit and a right-handed limit, but it's said to not have a limit. Okay? Because those two left-handed and right-handed limit are different. Okay? Questions about that? So in order for something to have a limit, the limit from the left has to equal the limit from the right. All right. So, moving on. We have this function, which is a piecewise function. For the function f, find the limit as x goes to 2 from the left, x goes to 2 from the right, and as x goes to 2. So the way you graph these piecewise functions is by plugging in, well, first of all, I know what shape this is. What is this? What shape is this? 2x minus 1. Hello? A line, right? But what you might want to do is plug in 2 into here, and I get out 2 comma 3, right? 2 comma 3, okay? And if I were to graph this, going over, this is my xy axis right here. I go over 2 and up 3, and I put an open circle there, okay? And I put an open circle there because that indicates that that point, let's see if I can make that a better open circle. That indicates that that point is not part of this function at x, because it's for x is less than 2. And it's a line with a slope of 2 and a y-intercept of -1. So what this says is from there and everywhere to the left of that point, okay, I have something that looks, ooh, it's going the wrong direction. I don't want it to go that way. All right, change that. Okay. Tool. This tool. Want to make, I guess it matters which way the arrows go. So, and I want to make it a solid line, I think. And I want to make it a colorful color. All right, so from this point and down through that point, my function's looking like that. Okay? And then at x equals 2, my function has a value of 1. So in other words, this is an open circle, but right at 2, I have a dot right there. And then anywhere after 2, it looks like this line, which has a slope of a slope of 1 and a y-intercept of -2. But the way you can figure out where it starts is by plugging into, what do I get out if I plug in 2 in here? 2, 0, right? So starting with an open circle at 2, 0, I know this line has a slope of 1, so after that point, it's going to go up like this with a slope of 1. So that's what that function looks like, all right? So now it asks you, find the limit as x goes to 2 from the left side. What value am I approaching as I approach 2 from the left side? 3, right? So that limit is 3. What's the value that x is approaching as x approaches 2 from the right side? Oh, should that be 0? Did I draw my graph wrong? Sorry. It should be up here. Sorry. Can I erase this? Let's see if it'll let me erase it. Whoa, squish out of the way, would you there? Okay. So it should be going open circle here, and then it should go up with a slope of 1 from that point. Sorry, I didn't really have a clear xy axis. Okay? So this value is 0, and what would be the limit as x goes to 2? dne, okay, because it's approaching a different limit from the left to the right, okay, and that's that. Questions? Okay. So next, we're going to look at these rules. It says a function is continuous. This is the definition of continuity, okay? This is an important word. A function is continuous if f is defined at c. That is, c is in the domain of f, so that f of c equals some number. Okay, so you can't have a hole in the graph at that point. The other thing that has to be true is that the left-hand limit is equal to f of c, and the right-hand limit is equal to f of c, and those left-hand and right-hand limits need to be the same. Okay? So to demonstrate that those rules, we're going to look at this function right here. Okay? As x goes to, or determine if x is continuous. Is it continuous at -2? Just looking at the graph, is it continuous at the -2? No, because the left-hand limit and the right-hand limit are not the same, right? And so the answer to this is no. No. Where's my... Do I have a value for my function at -2? What's the value of the... What is f of -2, if they ask you that? 2. It is 2, because it's got a shaded-in dot right there, okay? So it is defined at -2, okay? But since the left-hand limit and the right-hand limit are not the same, it is not continuous there. At x equals 0, does it appear that my function is continuous at that point? Yes, because it's approaching the same value from the left, it's approaching the same value from the right. It's defined there, and the value that they're approaching is the same as the value of the function. Okay? Now, let's look, so yes. Okay, it meets all three of those conditions. At x equals 3, are the left-hand and right-hand limits the same? Yes? Yes. Does it have a value at 3? What's f of 3? -1. But is the limit it's approaching the same as the value of the function? No, because the limit as x goes to 3, right, is equal to what? 1. Okay, the limit of f as x goes to 3 is equal to 1. But f of 3 is equal to -1. So in order for it to be continuous, the function is defined there, and it has a limit. But in order for it to be continuous, these two things need to be the same. Okay? So the answer to this is no, because f of c is not equal to the limit as x goes to c of f of x. Okay? So that's why, even though it has a value there. That, by a removable discontinuity. Ooh. And this is called a step discontinuity for your purposes. Okay. Then they do stuff like this. They'll say, those evil math butt people, it says, look at this rational function. Let's draw in some nice heavy lines so we can see where the x and y axis are. Let's put arrows on both ends of my thing. Okay? So here's the y-axis. Whoops, that was the y. Let's try to do that again. Do that again. Go straight this time. That's pretty good. And this is going this way. Good enough. All right. So there's my x-y axis, and determine the numbers at which the rational function is continuous. So in order to do this, I have to probably factor the bottom. Okay, and we've done this. We did this kind of first semester, but that factors to x what minus 4x minus 2. Yes. Okay. So this thing has a couple different things going on here. One thing it has in is, if I can do this, what does it have? It has a hole, okay, at x equals 2, and to find out what the y value is, I can just plug in 2 in here. There's a 1 here, right? 1 over 2 minus 4 is negative 2. Y equals negative 1/2, okay? So I know that at 2, comma, negative 1/2, there's a hole in my graph, okay? I also know if something makes the denominator undefined, but it has, but it doesn't cancel out with the top. What does this tell me that I have at x equals 4? What do I have? I have, very good. I have an asymptote, okay? I have an asymptote at x equals 4, okay? So if I want to draw in that asymptote, look, draw it in dotted lines in different color. At x equals 1, 2, 3, 4, I have a vertical asymptote, okay? And it says determine the numbers at which the rational function is continuous. Now, we did a couple things first semester where we looked at very big values and very small values. So let's look at the limit as x goes to the limit of f of x as x goes to 4 from the left side. Who can tell me what that is? As I come towards 4, where do you think I'm going to go? Down or up? Well, you can figure that out. You could figure that out by looking at 1 over x minus 4. This is a simplified. What's a number very close to 4 on the left side? What's a number very close to 4 on the left side? To the left of 4. 3.99, let's say, okay? So if I were to plug in 3.99 in there, I get 3.99 minus 4, which is 1 over what kind of number? Negative 0.01, right? Which gives me negative 100, right? So as I get very close to this thing, what's happening to my y values? They're going down, okay? So this thing kind of goes through this hole. It has an asymptote to the left, and then it goes down kind of like that, and approaches that asymptote. So that is said to be negative infinity, okay? The limit as x goes to 4 from the plus side, okay, of f of x. If I plug in a number very close to 4 on the right side, like 4.01, what kind of number am I going to get? A very big positive number, right? I get like positive 0.01 in there, and that would give me 100, so that means that I'm going this way as I approach that asymptote. Sorry about the bad curve, okay? So near 2 and 4, it's obvious that I have a hole there. It says use limits to analyze the function near 2 and 4. You can tell that as x gets close to 2, I am approaching negative 1/2, and I did that by reducing it and plugging in 2 into there, right? Okay? And so, graph R, we did that. Determine the numbers at which it's continuous. So you could say it's continuous for x is less than what? What number is that? Is it continuous everywhere past here? Or you could just say continuous when x is not equal to what? Not equal to 2, or x is not equal to 4. That would be kind of enough, okay? And analyze the graph, we kind of analyzed the graph. We said there's a hole at 2, negative 1/2, right? And we said that there's an asymptote at 4, and we looked at the limits here and here. Now also, you should look at the limits as x goes to negative infinity. As this, we kind of talked about this first semester. The limit as x goes to negative infinity of f of x. What's that? What value is this going to approach? 0. Remember that rule? If the denominator power is bigger than the top power, it's going to approach 0. What's the limit as x? Limit? Limit? I meant to write f of x. Limit of f of x as x goes to positive infinity. Hello? What's the limit as f of x goes to positive infinity? As this number gets very, very, very big, what happens to the whole fraction? Or as this number gets very, very big, what happens to the fraction? Hello? It gets very small, right? Think about it. The squared thing outweighs the linear part, right? So if I plug in 100 in here, right, it's going to be 100 minus 2 over 100 squared minus 600 plus 8, right? And if I plug in even bigger numbers, this thing is going to totally outweigh this and this and this. So it's going to look like 1 over a billion eventually or something like that. And so you're going to approach 0 this way as well. And that's why the graph looks that way. Okay? Yes? No? And lastly, I added in this little one. And because it's a little bit different, determine the values at which it's continuous. So I could just graph this up here. X squared of x is less than 0. So if I were going to graph this, let's draw on my axes again. Let's make it green. Let's make it solid. Okay. Oh, it's purple. That's even better. So x squared of x is, what does x squared look like? Hello? You know that it's a parabola. So what this function says is if x is less than 0 and including 0, I have a parabola which kind of goes up, it goes through these 2 points, and it looks kind of like that on that side. Okay? Starting at, and the way I get the starting point is by plugging in 0 in here. Okay? When I plug in 0 in here, what do I get into this bottom function? What? 0 plus 1? 1. So I have an open circle here at 1, okay? And then between 0 and 2, not including 2, I have a line with a slope of 1, right? And so it's going to go up this way. That's be an open circle. Whoops. Open circle there. And it goes up here until you hit that open circle. Okay, and it goes down here like that. I don't know. And then it has another line at x equals 2 and 2x equals 5. So when I plug in 2 in here, what do I get out? 5 minus 2. What do I get? 3, right? So if I plug in 3 in here, I can fill in that hole. You see that? Fill in the hole? See why I fill in the hole? Because if I plug in 2 into this function, I get out 3. And if I plug in 2 into this function, I also get in 3. So I can fill in that hole. And which way does this graph go? 5 minus x. Downhill with a slope of -1 until I get to 5 comma what? 5 minus 5 is 0 until I get to 1, 2, 3, 4, 5, 0. And that's a closed circle as well. So after that point, it goes like this, okay? So that's kind of a funky function, but it says determine the values at which it's continuous. Well, is it continuous at x equals 0? No. So you could say that it's continuous to the left of 0. It's continuous, where x is less than or equal to 0. It's continuous and then it's continuous from where to where? X is bigger than 0 and less than or equal to, what's this number? 5. Okay? So that's, for x is less than or equal to 0 going this way, and for x is greater than, well, it's not, I think you'd have to put just less than there, okay? Because it's not, since it jumps at 0, it's not continuous there, even though it's defined. So for x is less than 0, and for x is between 0 and 5, this function is continuous. Do you follow that? Kind of confusing, but it's kind of cool. I mean, that's kind of testing your conceptual understanding.